Good morning, everybody. Oh, that was nice. So we are going to talk today about calculating volumes of solids using integration. And so we're going to start by talking about calculating volumes using known cross sections. And this is where you take a given function. So you're given some sort of function or figure. And then what's going to happen is that you are going to take this function and it's going to be used to model the base or one of the sides, the radius, so forth, of some um, perpendicular figure. And then these perpendicular figures are going to change as the function changes. And if you were to take these infinitesimally tiny perpendicular figures and put them all along the length of that function where you're interested, you end up with a three-dimensional solid. So you're given this function. You're also given a cross section. And so this is going to be some figure, maybe for example a rectangle or a square, so forth. And then what you're interested in doing is you're interested in asking yourself, how can I use this function to model, say, one of the sides or the radius, or let's just say the information needed to calculate the area of my cross section. And so then what you're going to do is you're going to think about all the information that you need in order to calculate the area of this cross, or the area of this figure, this given cross section. And you're going to write a formula. And the formula, generally we would call it A, is going to use the function. No, okay, let's say something else actually. You're going to use the formula for the area, and you're just going to integrate it within your bounds. So say it was a square, then you would need some sort of function that would model the side of one of those squares, and then your area function would just be one of the sides of those squares squared, because that's the formula for the area of a square. And then you take this and you integrate it over your given bounds. So let's take a look at an example. I think pictures are incredibly helpful when you're doing this. And I know it's hard to draw three-dimensional pictures, but you just have to do the best you can. So I don't have a given picture for this one, so I'm going to try to sketch one out. So they tell me that the base of this figure is a circle. And so it's the unit circle. It has radius 1. It's a pretty horrible circle, but we'll do what we can. And they tell us, we know that that's 1, 1, negative 1, and 1. Negative 1, sorry. And we're going to take cross sections perpendicular to the x-axis. This is important. Whatever axis you're perpendicular to, this is what you're integrating with respect to. So I know that I'm going to be integrating with respect to my x-axis. So I'm integrating with respect to x, and I will need a function with just x in it to model the, probably the kind of diameter, or sorry, it's going to be the base and the height of my triangle, since they're equal. So they tell me we want this triangle whose base and height are equal. And so the base of my triangle, if I'm taking these cross sections perpendicular, is just going to be the length along the square, or the circle. It's kind of early, sorry. And so this is my lovely attempt at a three-dimensional drawing. So here's going to be my cross section. So I need to think about how I can write an equation that will model this base. So I need some equation to model the base. So I know the equation for this circle is x squared plus y squared equal 1. And if I were going to take and I were going to write this equation in terms of x, because I need an equation in terms of x because I'm integrating with respect to x, I would get that, let's say, the top half of my circle is going to be the square root of 1 minus x squared. I just take that and solve it for y. And so that's going to model this area, that right there. And then I have equal area down here. So I think that, or I have, it's symmetric about the x-axis. So I think that I can model the entire circle by just taking, this length, which would be or the square root of 1 minus x squared, and then doubling it, because that'll give me that length down there. Since it's volume, I'm not concerned with the negative area. So now I can write this equation for the entire base of my triangle that's just going to be double this function. And now I need to write an equation for the triangle because this is the equation for whatever figure you're using as your cross section is going to be what you're integrating. So for my triangle, it's just going to be 1/2 times my base all squared. Because it's usually 1/2 base times height, but my base and height are equal in this case. So this right here, I can plug this formula in for my base, and then I'll have a function that I can integrate. And I need to look at my bounds. So if I'm integrating with respect to the x-axis, or integrating with respect to x, then my bounds are just going to be my x bounds, which are -1 to 1. Right, so I've determined the formula for my cross section. I found a function in terms of x, since I have cross sections perpendicular to the x-axis, that will model the base of the triangle. And now I'm going to plug that in and I'm going to integrate within my bounds. So my integral will look like this, -1 to 1. And then my formula is 1/2 times my base, which is 2 times the square root of 1 minus x squared, all squared dx. And then I will simplify a little so that it's not so difficult for me to integrate. And I end up with, this is going to be 4 times 1 minus x squared, so that'll become 2, and I'll put that on the outside, times 1 minus x squared dx. And then now, it's simple. I mean, you guys know how to do this. So this is just going to be 2 times x minus 1/3 x cubed from -1 to 1. And if I plug in and do all the math, I get 8/3. So the volume of that solid with these known triangular cross sections is going to be 8 1/3. It's a pretty strange image to think about, but it's going to be pointy at the top, it's going to be smooth on the bottom, and I think it should kind of decrease on either side because the base of that triangle will decrease as you get closer to the edges of the circle. I'm definitely not a spatial person, so sometimes I have difficulty imagining the pictures in my head. All right, so let's try another example. So here we're given two functions. So they say the base is the region enclosed by x squared and y equal 3. So I've given you a graph of this, and the cross sections are perpendicular to the y-axis. So that means I'm going to be integrating with respect to y, and they're going to be squares. Squares is a nice, easy formula. So my squares, the formula for that is just my base, or one side, squared. So what I'm going to do is I'm going to attempt to do this. Oh, that's nice. So since I'm integrating with respect to y, I've taken my picture and I have, um, I've rotated it. So now this is my y-axis, remember? And this is my x-axis right there. So I'm going to make these squares, and then I need to figure out the length of the base, and they're going to go in between this line y equal 3, and then since my function stops at 0, I can already see that my bounds are going to be 0 to 3. So I'm going to go ahead and write that down. These are y bounds because I'm going to be integrating with respect to y. So I need, since I'm integrating with respect to y, I'm given this function y equal x squared. And I need to write this and solved for x because I need a function in terms of y. So the top half of this, which would be, I guess, to the right of the y-axis, or the one that's on top in the picture we're looking at, is just going to be the square root of x is equal to y. So I can see that this thing is symmetric about the y-axis, so the distance, I wish my picture was just a little bigger. Ah, there we go. So let's see if I can do this now. So this distance right here is going to be the distance, the square root of x. So kind of similar to the way that we did the circle problem before, the bottom is going to have the same distance. So I can find the total distance by just taking that distance, the square root of x, and multiplying it by 2. And this is going to give me the base or one of the sides of the square that I'm going to create. So I can say now that my side is going to be equal to double this function, so it's going to be 2 times the square root of x. So I've actually now built all the pieces that I need. Oh, that's strange. So I found the formula for my square, because this is what I'm going to be integrating. I found my bounds, and then I have found a function that models this side that I need. So now I just need to plug in the formula for my square into my integral, plug in my function in terms of x for the side, and integrate within my bounds. So this is going to be the integral from 0 to 3, right? Oh, I just realized it's early. So I need a function in terms of y, and I'm not quite sure why I thought that I could write this way. I'm sure you guys are all laughing at me. Let's just be the square root of y is equal to x. That makes a lot more sense. All right, so I have this side. I'm going to plug it in to the formula for the area of my cross section, which is a square. So that's just one side all squared. Integrating with respect to y, so I'm going to clean it up a little. The 2 is going to become a 4 because it's squared. To pull the constant out front. Root y squared is just y. So this is a pretty easy integral, actually. So now let's take and let's find our antiderivative. It's just going to be 1/2 y squared from 0 to 3. So the area is just going to be 18, or the volume. I apologize, the volume. So it's not that difficult. You just have to, find that function that models the piece of your figure that you need, and then integrate the formula for that figure within your bounds. So I have one more. This one's a little tricky. So we actually are going to kind of need to create two formulas. So what they've done is they've given us the figure for the area of an ellipse, which is pi AB. A and B are the lengths of the semi-major and the semi-minor axes. So this would be my semi-major, and then this right here, if I can get it on there, would be my semi-minor. And we want to compute the volume of this cone with a height of 12, whose base is an ellipse. And the base has a semi-major axis of 6 and a semi-minor axis of 4. So what we need is okay, so let's do this first. The first thing I would do is I would put a set of axes on this because we're going to need a function. So since this thing is turned up in this way, what I'm going to do is I'm going to make this my y-axis, the height of the cone. And then I'm going to make kind of this piece right here the x-axis. So I can already see that if I want the volume of this cone, it's kind of a cone, the bottom's not circular, then I'm going to be integrating from 0 to 12. So if you see a piece of information you have, just go ahead and write it down. Now I know the formula for my ellipse. They gave it to me in the problem. And my cross sections are ellipse. You can see that they've drawn this cross section in for you. So the formula for that is pi times a times b. So now I see that since this is my y-axis right here, and my cross sections are perpendicular to that axis, that I'm going to be integrating with respect to y. So I somehow need functions in terms of y that'll model both the semi-major axis A and the semi-minor axis B. So one nice thing about cones is that we can use similar triangles. So I can actually take and write an equation for the semi-minor axis and the semi-major axis using these right triangles. I've kind of drawn all over this. So let me erase it so it'll be easier to see. So I'm going to take one right triangle that's going to look like this. And then it would be similar to this right triangle right here, which, if I did it correctly, would give me half of the semi-minor axis. So since these are similar triangles, I can set up a formula. So let's see what I can do. So I know if this right here, oops, sorry, so I can get it right, is the distance between my figure, my cross section, and the y-axis, then this right here is going to have a height of y. So then I can find the height of my triangle. So let's say smaller one. Let's call this triangle the smaller one, and then the whole thing the big one. So then I can already find the height of my triangle, and it's just going to be 12 minus y. So this is going to be the height of my triangle. Now the base is going to be this semi-minor axis, and they called this, funny enough, the semi-minor was B. I think that was B. Now for the big one, I have numbers for this. So I have that my semi-minor axis, which is going to be, half of my semi-minor axis, which is the base of this triangle, is 2. So the base is 2. And then they tell me the height of the whole triangle is going to be 12. So now what I can do is I can take and I can write an equation that will give me, I can set up similar triangles. So I know that 12 minus y over b is going to be equal to 12 over 2. So I can cross multiply. This is going to be 2 times 12 minus y is equal to 12b. So that means that 1 over 6 times 12 minus y is equal to b. So now I've kind of got half the work done. I've taken and I've written a formula for b that's only in terms of y. So now let's take and let's do it for the other side. So now this is my triangle. This is my smaller triangle. And so I'm just going to erase what I wrote here so I can fill it in for the other. The height for this thing is still 12 minus y, so I guess I shouldn't have changed that. But the base is now going to be the semi-major axis. So for my smaller one, let's say the height is still 12 minus y. And the base now is going to be half of the distance, half of the distance of my semi-minor axis. So I actually screwed up the other one. This should be 1/2 A. And for my big one, the height is 12, and then the base is going to be half of my semi-major axis, which is 3. So now I'm going to set it up. I guess I should fix this one. This should be 1/2 B. So that makes that 6 right here. So this is going to make this 1/3 over here. All right, so this is going to be the No, I think I might be doing the math wrong. I got to check this. I'm very sorry. Nope, I was right the first time. So B, I was right the second time actually, is 1/3 times 12 minus Y. Okay, so now we're going to do A. So we know that 12 minus Y over 1/2 A is equal to 12 over 3, which is 4. So now we're going to take, and so this means that 1/2 times 12 minus Y is going to be equal to A. So now I know A, I know B, I know the formula for this ellipse, which is pi times A times B. I know my bounds, so now I can set up my integral. So I'm going to be integrating from 0 to 12, and then I'm going to just put this pi on the outside, and then A is 1/2. Pull this up so I can see. 12 minus times 12 minus Y. And then my B is 1/3 times 12 minus Y. So I can clean this up a little bit, dy. So I'm going to pull this 1/6 out. So this is going to become pi over 6 on the outside. And then this is just going to be 12 minus Y, all squared dy on the inside. So now what we're going to do is we just integrate. So this becomes negative pi over 6 times 1/3 times 12 minus Y to the cubed from 0 to 12. So now I can take and I can plug everything in, and I get a volume of 96 pi. All right, well, sorry I kind of botched the last problem, but I hope that you guys learned something about cross sections, and I will talk to y'all soon.